Alright then, good evening. My name is Mohammed Gatalhak. I will today be talking about the first assessment of MEC 4406, which is robotics and machine vision. This assessment is talking about the context of designing a robot arm, and I have a physical one and a virtual one. I will start firstly by talking about the virtual one, then I will get to the physical one. So just I will describe the code quickly before I get to run it, and then we will go into the operation process of it. So we have the class robot arm 2D. After we get the imports, of course, input for the plot, import for the plot, and input for numpy. We have the class robot arm 2D, just so we know that we are looking at a 2D plane here, and it's basically storing link length in self link length and storing the coordinates 0 and 0 in self joint angles. Then we have our forward kinematic mathematical operations inside this function, and I can get that one in here. One second, I will get the forward kinematic in here. So the forward kinematics calculated is taking the input of the joint angles θ1 and θ2 and link lengths L1 and L2, and outputting the position of the end effector, which is x2, y2. x2, y2 will be the desired coordinates that the user have entered. Now, to calculate the position of the first joint, which is x1, y1, we use L1 multiplied by cosine θ1 and L1 multiplied by cosine for y. We use also L1 multiplied by cosine θ1. It's the same thing for x1 and y1, basically same function. For the position of the end effector, we have the x2 and the y2, but equaling x1 and y1 plus L2 multiplied by cosine the sum of θ1 plus θ2, and the same thing also for y. 2, it's L2 multiplied by cosine θ1 plus θ2. Now then we get the inverse kinematic function, I think. Before the inverse kinematic, we have set the joint angles to expect the values of self end angles, and we put angles to be stored inside self joint angles. Alright, then we have the function for plot. It's basically defining the self forward kinematics, putting it into positions, storing it into positions, we defining the x and the y coordinates into z positions. We have the plot, which is the plot for the grid. We also have set the values which x and y are expecting between -100 and 100, positive 100. We have the grid and all stuff related to showing basically the grid or the squares, like the squares where the robot will stand on. Then we have here the inverse kinematic mathematical function, which to get back to here, basically how it's calculated, we get cosine θ2, start by getting cosine θ2 by x squared plus y squared minus L1 squared minus L2 squared. All of that is divided by 2 multiplied L1 multiplied by L2. Then the value that is in here, we will use it later into this function, which is the getting the θ2. So we also use the value from sine θ2, which is square root of 1 minus cosine θ2, all of it, all θ2 squared. So we use the values from this one, this equation and this equation into here, the tan, inverse tan, for referring here for those two values, because they are the coordinate consists of x and y values, and this is how we basically get the theta 2 value. Now in relation to x and y. Now for that one, we also to find theta 1, we use a the variable k1 and k2, where in k1 it equals L1 plus L2 multiplied by cosine theta 2, and k2 equal L2, which is also the length, multiplied by sine theta 2. Now theta 2 we got it from up here, and all of these depends on the values entered by the user. For then finally to get theta 1, we use the inverse tan of both of those values also to get the respective x and y. But in this case we've started with y and x, and then minus is subtracted from the inverse tan of the k2 and the k1 which we got. So we will use the x and y which we got them which we have been given, and the k2 and k1. Now to get back into here, we can see that it creates the robot arm with two lengths of 50 millimeter, and this is an example length. This is not necessarily like a true life application, but we said that that they will be 50 the joint lengths, and not forgetting of course that it operates in a 2D environment, and the coordinates need to be reachable within the range of the robot arm, and this is a node, and it moves here the robot arm to the coordinates on the chessboard, and this is where we're going to enter the coordinates and plot the robot arm's position. It just plots it on here. So for example, I will just go and do negative let's say 75, and I will go put here let's say I want to put 50, then click run, and here it is. We can see negative 75 and 50, the lost coordinate. Let's say we want to do something like we want to do like, let's say 75 and 75. I don't know if that it will allow us, because it should I think it should allow us, because oops, sorry, 75 because they are within the range of the values. Yeah, I don't think it will allow us, because it's not within the, because if one joint if it's 75 and 75, okay, let's try and do 50 and 75. Yep, I see. Okay, let's try and do how about if I need to get it to 100? Can 100 work, or 99 work? Not 100, so because 100 is the limit, I think. I don't think so. So how about 90? Alright, so can I try and increasing that to 60? Also no, it's not accepting it. How about 80? Alright, it needs the value needs to be something that fits into this equation, which is sine angle, the second angle, and then put the square root 1 minus cosine angle. Alright, then how about I put a value of 50 and I run? Oh, that's interesting. So when I did put the value of 50 in this coordinate it did it, and in y coordinate, and in the x coordinate put 80. Nice. Alright then, how about if we wanna go higher, can we go 60? That's also very nice, because the reach of the thing is considerably like limited within the functionality. So can we go up and go 70, or will it error? Yeah, it will error. So if the only part it can stop to when it's 80 is at the in the x, it will be at y80. So how about if I increase this to 90?
So this is the second part of the recording. In here I will be discussing the physical robot arm, and continuing on the first one where I was discussing the virtual. So for that one, it runs on the same code as the virtual one. However, it has been translated by initializing onto that Brickman version 0.10 and the EV3 platform by initializing the motors and initializing all the libraries and the definitions that are needed to run the arm and operate it. It should be noted that the hardware and the parts were limited, so it wouldn't display the coordinates very accurately. However, it runs by the same way. So in here, I will just show that. In here, it basically, this is the same code, and I will provide it, and I will provide that in the Word documentation. So I will just, all what I will do, I will put in like how in the virtual code, I will put in the x and y coordinates. So in here I will put number negative 25 for the x, and I will put 20 for the y. Then I will click download and run. Then this hopefully loads. Oh, this one was 1 second. This one was a bit 1 second. Let me try bigger number than 20 for the y coordinates. Let me try that again. Sorry, just having some technical difficulties. Well, in here it I think it did move. Let me try another number, because this one did not move as expected. Negative 25. Sorry, I was facing some technical stuff here. Let's try negative 25 and see how will it go. Okay. because it only accepts numbers between negative 100 and 100. And here this is the second time, and it will continue having this issue because we didn't have enough rails to make it extend and come back. However, this is just to show the concept that it's moving. Should be noted that the same inverse and forward kinematics for the virtual one was used into the physical one, so I did not change any of the matrices involved or any of the calculations. It has been the same. A copy of the code for that one will be also provided in the Word documentation. Thanks for taking your time to have a look at this assessment, and yeah.